Hello, it's Keith here, and this is lesson 4 of the Photon series of my 6502 assembly programming tutorials. What's the Photon series? Well, it's my little Tronco, and you can see it now. It is really small there. Not great, but we'll try and cope with it. So basically, it's a very simple Tron game here. You can see we've got our light cycle. The enemy is CPU controlled. We can move around. We've got some obstacles. We also have something called boost mode, which is where we move super fast to try and catch up with the enemy. The other thing is the cursor controls. If I press a direction and hold it, it waits for me to release so that I don't accidentally collide with myself. Now that's it running on the 5200, but as usual, it does also run on the Atari 800. You can see it just there, and now I've got different controls I need to contend with. There they are. But the game is identical on both, so it's been ported to both systems quite effectively. Now we're not going to cover the code that's the same as before. A lot of the code's been transferred over from YQuest and even the simple series, so I'm not going to cover the joystick routines and the screen initialization routines and all of that kind of thing because I'm quite bored of them. What I'm not bored of is the pixel plotting routines, which are new for this one. This is really the point of this series. It's about how to plot pixels rather than draw bitmap sprites as blocks. So that's what we're going to be looking at. Well, let's go over to the source code and let's take a look at it. Okay, so here's the start of the code. So the first thing you can see here is we've got some code here that's defining the screen because this is multi-platform, most of the code, so we need to set the system up. Now the screen is effectively 160 by 192 on this system, so not as wide as I'd like, but it's okay, and the colours are quite nice. There's 4 colours on this system, but the game is designed to work with up to 5, one background colour and 4 other ones. So in this case, colour 4 is being remapped to colour 1. So that's how I get around that for the systems that don't have enough colours. And then we've got, as always, we've got different versions of some of the code for the Atari 800 and 5200. We've then got our screen initialization here. Please see the simple series, the bitmap series, or the platform specific series if you need to know how that works. I'm not covering it here. What I'm going to cover is the code that's specific to this game. We've got the initialization of clearing the user RAM here. There's about 256 bytes of user RAM just defined here. Different location on every system, but the same number of bytes. And then we're showing the main menu. And then we get into the main game loop here. Now, the game works in ticks. There's 2 ticks. In boost mode, you move every tick, and in normal mode, you move every other tick. So that's how the game is being controlled speed-wise. Now, when boost mode's on, we have to update the boost counter in the corner, and unfortunately the code that does that, it's a vector font, it's not fast. So the delay is different depending on whether we're updating that boost counter or not, unfortunately. Slightly embarrassing there, not great coding, but it was a bit of a rush, and I really wanted that vector font because it meant this game's very easy to port to new systems. You need to create a new point command, a new PSET command, and that's pretty much it. So the vector font has pros and cons. Anyway, so we're using D here in the 0 page as a storage for any key presses, and we're reading the keys in here, and then we're checking if any keys are pressed, and if they're not, we're clearing what's known as the timeout, and this is how we check if the key's been released, because we don't want to keep processing keys if the key's held down. So the player will keep turning around and crash into themselves, which won't be good. So that's what we're doing there. We're looping around here. We store any keys that are pressed in D, and we will process those later on. Now here's the start of the drawing routine. We're checking if that key timeout is still set, and if it is, then we don't want to process any keys, so skipping over the next section. What we're doing next is we are setting boost to 1, which actually turns it off. Boost 0 turns it on. That's the way this works. We're then loading IX with the player X acceleration memory address, and the reason for this is set player direction. If the player's moved, we'll update those accelerations so the player moves in the correct direction. We're then checking 0 page entry D here, which is the current joystick input, and then we're testing if the player has turned left or turned right. If the player's turned, we're going to decrement or increment player direction, which is one of the 4 axes, north, south, east or west. And basically, once we've done that, we're going to copy, via set player direction, the new movement speeds into the acceleration here, which is why we're initializing that here. In both cases, we're setting the timeout so that the player doesn't collide into themselves. What we're doing next is we're checking the fire button. If the fire button is pressed and the player still has boost power, then we're setting boost to 1 by setting it to 0. The drawing of the player, the boosting and all that kind of goodness is done in the handle player routine, and the CPU AI and all the collision detection for the CPU is done in the handle CPU routine, and that's the main loop. We're just jumping all the way back up here. So that's really all of the code. The rest of it's multi-platform code, so we're not going to cover that here. The really interesting thing, I think, is the PSET routine and the point routine. Now on these 4-color bitmap systems, I've got this sort of common way that I do things. So basically what we're doing here is we've got A and B in theory here as the x-axis here, but this system doesn't need 2 bytes, so we're just using B here. We are just checking if we're trying to draw off the screen here, because sometimes that does happen with the boost position. The starting drawing position is actually off screen, so we're just correcting that there. And then what we're doing here is we are using this get pixel mask function, and what that's going to do is it's going to return a memory address of the byte of the screen that we want to change, and it's going to store a mask in 0 page entry D for the pixels we want to keep within that byte, because of course there's going to be 4 pixels in that byte. And then we're going to OR in the mask for the color that we want to actually set, and that's going to be in E. Now when get pixel mask runs, it's going to return a mask for the pixel we want to change, but it won't be in the right color. Get color mask number will get the right color for the color we want to use, and then we combine that via an AND command with the pixel we want to change, and the result will be the correct color in the correct position. I know this is a pain, but this is the way I've been doing it. It's easy to port. It's probably not the fastest way of doing things, but it is easy to port. So that's what we're doing there. Now we're basically using those masks here. We're loading in the current byte from the screen, masking to keep the pixels we don't want to change, ORing in the pixel we do want to change, and then storing it straight back to the screen. And that's the PSET routine, and we're going to cover this in a moment because of course this is doing a lot of the work. The point routine, kind of similar. We're using get pixel mask again. We are then reading the byte in from the screen as before. This time we're ANDing the pixel that represents the pixel we want to look at, because before we were changing it, but now we're looking at it, and that's going to return a byte with 2 bits somewhere in that byte set, and we're going to need to convert that into a color number, because although in theory this game just works on black and not black, I was trying to do a better job of that and actually give something that returned the same color pixel that was read in. So what we're doing here is we're taking that byte from the screen, and we're using a function called byte to color mask, and that will convert a byte that contains 1 pixel within it set to a color to a byte where all the pixels are set to the same color. And this can be also used for like shifting an object by 1 pixel or something. But what I'm using it for here is to use it as a reference against color lookup, which is the set of bytes here where each pixel within this, all 4 pixels, are set to either color 0, color 1, color 2 or color 3. And so this is converting that to the matching format of that lookup, and then we're comparing to that lookup. We're looking at the entries in, and we're finding the correct color. So we're increasing Y until we find a match, and then we're turning Y here, and that will now be the color that was read in from the screen. Okay, so we've got a few things we need to discuss then. So get color mask number is very straightforward. All it does is it uses the color lookup here, so we're passing a color in the accumulator at this stage, one of the 4 colors 0, 1, 2 and 3, and we're returning the byte from this lookup table. Get pixel mask, well, it also uses a lookup table, uses this one here, but it also uses get screen pos, and this is the code that was used in YQuest to calculate a byte position of the screen. So I'm not going to cover it here because I've covered it in YQuest and in the simple series, and I also covered it in the platform specific series. So if you don't know, please take a look at one of those. So that's calculating the byte position, but we still need that pixel position. So we're then taking the bottom 2 bits here that we removed when we ran this one, because this was ignoring the bottom 2 bits. This is looking at those bottom 2 bits, and it's using them as the position within this lookup table, and these are the 2 bits that represent each of the 4 possible pixels within a byte. So that's the leftmost pixel, that's the rightmost pixel, and you can see they're just nice and next to each other, which is the better way. Amstrad CPC Mode 1 does them in a terrible way, which we won't discuss, but anyway, this is nice and clear, very easy to work with, so I quite like that. Anyway, we're loading that in here, we're storing that in 0 page entry E, flipping all the bits with this EOR, and that's giving us now the mask for the background, which is the bits we don't want to change, and we're storing that in D, and then we're returning. And that's really all there is to it. So there we go. Now the final one is the byte to color mask function. As I say, what this is doing is it's converting a byte where 1 pixel is set to a byte where all 4 pixels are the same color, and it's taking an X coordinate because it needs to know where the pixel is that it needs to fill. And what it's basically doing is it's repeatedly bit shifting that pixel, and it's then ORing in to make a byte that is completely filled. Now I'll be honest with you, this isn't possibly the best way of doing things. What I think would be better on this system would be to take the X position and then bit shift accordingly, because which of these 4 pixels it is, if we shift it to the right enough, the final result will be a valued number from 0 to 3, which is what we want the point routine to return anyway. Now the reason I'm kind of doing it this way is it was for the Amstrad CPC, where the mode 0, for example, was terrible. The layout of the bits compared to a number from 0 to 15 were ridiculous. This is far better way of doing it on that system. It's not so great on this system, but it means it's very easy to port to other systems, so that's why I've done it like this. We've then got the stuff that's been covered before in YQuest, the joystick reading routine. Here we've got the display list. This is the table for the screen mode. If you wanted to do this in 2-color mode, I think you could convert it. I'm not going to, but I think the code is probably, the code is kind of still there. You'd need to rewrite some bits of it, but I don't think it would probably take too long to get this to work at a higher resolution. You just need to change those PSET routines a little bit, but as I say, yeah, the graphics routines do still work in 2-color mode, but as I say, I think this is more appropriate as a 4-color mode. A bit of color it never hurts anyone. And there we go. So that's the end of this lesson. As always, you can go to my website and you can download the source code and you can have some fun with it, hopefully, and maybe you'll be able to make something better than me. And if you can, good luck to you. I totally encourage you to do that. Anyway, if you've liked this video, please hit the like button and subscribe, because if you like the videos, YouTube recommends them to more people, and maybe I'll get a few hits for a change, because I don't get very many. And if you subscribe, it encourages me to keep looking at more crazy systems and writing tutorials for endless machines that I've never owned and are 30 years old anyway, so it keeps my motivation up. Anyway, I hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.